right, so now I want to put together everything that we've practiced and try to sketch a graph for a rational function. So in this case, I want to graph f of x equals x squared plus 1 over x minus 2. You want to start off primarily looking for any asymptotes in this graph and the x and y intercepts. Those are going to be the main clues that you want to pull together to sketch the graph. So I'll start with vertical asymptote. Oh, and keep in mind any holes that might occur in the graph. So vertical asymptote, remember you first need to simplify. So look for common factors in the numerator and the denominator. In this case, both the numerator and denominator are in their simplest form. They can't be factored further. When you have x squared plus a number, you can't factor that. If it's x squared minus a number, you could factor it as a difference of squares, but not if it's a sum here. Then that only has imaginary zeros, so we're not going to bother factoring that. So to find the equation of the vertical asymptote, you set the denominator, in this case x minus 2, equal to 0. So the equation of the vertical asymptote is x equals 2. So if I find 2 on the x-axis, so that's right here, I want to put a dotted line at x equals 2. I'm sorry, my family's kind of loud in the background. Like obnoxiously loud. Okay, vertical asymptote at x equals 2. Now, non-vertical asymptote, which may be either a horizontal or a slant asymptote. That's where you compare the degrees, so the highest power in the numerator and the denominator. This function has a higher degree in the numerator. So it's one of those top-heavy functions. So when we're considering does this thing have a horizontal or a slant asymptote, we're comparing the degree of the top and bottom. This is one of those top-heavy functions. So to find that tells us it's going to be a slant asymptote, and to find the equation of that slant asymptote, we need to divide the top by the bottom. So we need to divide x squared plus 1 by x minus 2. So that division is eligible for synthetic division. So I'm going to use synthetic division because it's a bit faster. You're welcome to use long division. One thing about using synthetic division on this, you need to include coefficients for every power of x starting with your highest power. So notice how this skips x to the first, so we're going to need to insert a 0 coefficient for x to the first. So when you write your coefficients for the numerator, you need to write 1 representing your 1x squared, and then 0 representing the fact that there is no x to the first, and then 1 for your constant term. That's an easy part to mess up. Okay, so we're going to do this division. I bring the 1 straight down, and then I do 2 times 1, so that's 2. Add these numbers together. And really I could stop here because we don't care about the remainder, but I'm just going to go ahead and finish it. So 2 times 2 is 4. Combine these, so the remainder is 5. But what I was saying is, in the equation of the slant asymptote, we take just the quotient. We ignore the remainder. I know it's x to the first plus 2 because this is x squared divided by x to the first, so that leaves x to the first for my quotient. So this is the equation of the slant asymptote. Now, I may not have graphed those yet in a video that you've seen, so let's talk about that. We need to graph the line y equals x plus 2. The way I would think about that is think back to your old slope-intercept form, y equals mx plus b. So in this case, your slope, m, is 1. So in terms of rise over run, that's 1 over 1. And your y-intercept, b, is 2. I was going to write 6 because my b right here looks like a 6. I'm confusing myself. Y equals x plus 2 is what we're trying to graph. So the b, the y-intercept, is 2. Okay, so this is going to hit the y-axis at 2. I'm going to put a few more hash marks on here right now just because we're going to need them later. Go ahead and insert these. Whoops, getting a little sloppy. Okay, so this slant asymptote has a y-intercept at 2 and a slope of 1. So it's going to go up 1 over 1, up 1 over 1. And just, I'm going to do several dots here because I have trouble, especially electronically here, sketching a straight line. And I'm going to go backwards also, so like back one, down one, continue this line backwards a little bit from that y-intercept. Okay, so I mean there's pretty much, that's already pretty good. So this is the slant asymptote right here. This is the y equals x plus 2. All right, so we've got our asymptotes on the page. The other thing that you should get on the page before you start sketching are your intercepts. So you find the x-intercepts by setting the numerator equal to 0, the top. So in this case, that's x squared plus 1 equals 0. But we've seen this a few times in this lesson. If you have x squared plus a number, that's not going to have real zeros. If you move the 1 over, you have x squared equals negative 1. That doesn't have real solutions. So this tells us, I mean, you don't need to despair though. This is actually useful information. We know now that there is no x-intercept. So when we draw the graph, your graph should not cross the x-intercept anywhere. Our graph can't touch the x-axis based on our work here. To find the y-intercept, you should plug 0 into the function. So the function was x squared plus 1 over x minus 2. And I went ahead and made the x's zeros. So this is 1 over negative 2. So the y-intercept is at negative 1/2. I'll draw the graph in blue. So the y-intercept is at negative 1/2 right here, or about there. Okay, so this is what we know about the graph based on asymptotes and intercepts. We got our asymptotes written down. We've got 1 point on the graph, so we don't have a ton of information. And this last part is the part that does tend to cause students trouble, so I'll try to go nice and slow here. Although I'll say one thing, it helps to just be familiar with the general behavior of the graphs of these rational functions. So the more you do, you're going to start to be able to visualize the graph more and more easily, because they do all follow similar patterns. So one thing here, I have this point on the graph. I know the graph cannot cross its vertical asymptote. And the graph can't go up above the x-axis. We know there is no x-intercept. So putting those clues together, I know that this section of the graph looks something like this. It's going to stay trapped by those asymptotes, and it's also going to stay trapped below the x-axis. So something like this for the left portion of the graph. Now also notice that this portion of the graph, so this covers all x values from negative infinity up to 2. Right, so it covers this side of the domain. Now we need to draw the portion of the graph that covers x values from 2 to infinity. That's the other portion of the domain. Remember, domain for these rational functions is all x values for which the denominator is not 0. So in this case, everything except for 2 is in the domain. We drew a graph that covers all the x values less than 2. We now need to draw a graph that covers all the x values greater than 2. Now, based on, like I said, it's learning the general behavior of the graphs of these rational functions. If you've looked at some graphs of rational functions, then you'll know that you kind of have two options on the right side of this graph. It's either like this. Actually, let me use a different color so I can say it's the blue curve or the green curve, that sort of thing. So the options on the right side, it's either this, like I'm drawing in red, or it's going to be like this, what I've drawn in green. And to determine which, what we really need to do is pick an x value to plug in on this portion of the graph and see if the y-coordinate looks like something that would lie on this red curve, or does it look like something that would lie on the green curve. And it's just a question of, should the graph be above that slant asymptote or should it be below the slant asymptote? I will say one other thing though. We know there's no x-intercept. So we kind of know it can't be this red option, because then there would have to be an x-intercept. It's going to have to cross the x-axis right there. So that kind of tells us that it can't be the one in red, and so the green graph is going to be the correct sketch for the right side of this graph. Although I'm going to also, sometimes you do have to just plug in x values, so let me demonstrate that. So you'd want to pick an x value that's to the right of this vertical asymptote, which is at x equals 2. So pick something to the right of that, like let's say x equals 4. And I'm choosing that. That's kind of an arbitrary choice. You can choose anything bigger than 2, and that would be fine. All right, so I'm going to plug 4 into this function. So 4 squared plus 1 over 4 minus 2. So that's 16 plus 1, 17 over 2. So that's 16 over 2 would be 8, and then you'd have 1/2 left over. So that's 8.5. So yes, when x is 4, 1, 2, 3, 4, here's 4. The y coordinate is 8.5. So that's definitely up here above the slant asymptote. If you plug 4 into the y equals x plus 2, you get 6. So the y value is greater. It's going to be up here. If you at least have your curve written in the right, I'm going to call it a quadrant, then that would be fine. So as long as you have your curve sketched above the slant asymptote, then you'd be good. Yeah, and let me be a little more precise. So if I'm grading a graph that you guys draw by hand, you must have the vertical asymptote drawn as a dotted line in the correct position, which would be x equals 2. You must have the slant asymptote drawn in the correct position. So y-intercept at 2 and then a slope of 1. And then you must have your intercepts graphed in the right spot. So a y-intercept at -1/2 here. And then for the rest of the sketch, you just need it in the right region of the xy plane. So you would need the left side of your graph to be in this region, below the slant asymptote, below the x-axis, and to the left of the x equals 2, like this. And then when I'm grading this side, just one thing I always check for is make sure your graph doesn't cross the vertical asymptote. That should definitely not happen. And your curve should be up above the slant asymptote up here.